So, hello, I hope you're all doing well. I want to present some of our recent work in our group about new formation scenarios of massive black holes. These are ideas that we pursue since a few years, and they're based on a couple of established results that we've learned about the early universe. One of the things that we learned over the last 10, 20 years is that fragmentation is quite common in the early universe. It's very, very hard to avoid. It could be quite difficult to have a scenario where like direct collapse, where everything goes into one single object. It's much more likely that gravitational collapse, at least initially, leads to star clusters and to fragmentation. And the question is then what happens with the fragments. And of course, these fragments are unlikely to be isolated. The early universe has a lot of gas, and also these protostellar clusters that form are likely embedded in gas. So that is something one will have to take into account. And one will have to look at the interaction between the gas and the protostars. The gas can provide a gravitational potential. It accelerates the motion of the stars in virial equilibrium. They should move faster. The crossing time will be shorter. There could be more collisions, but there's also accretion of the gas onto the stars. This can change their masses, the radii, and also the orbits, so it can make very significant differences. We've been looking at this with simulations with the AMUSE code, where we were considering different scenarios for the accretion. We considered that in all cases there was a gas reservoir and the distribution of stars goes following a Plummer sphere. In some scenarios, we assumed that the gas reservoir was virtually infinite, so that whenever you accrete gas on protostars, the gas is replenished from the outside and the gas mass is then just constant and the stellar mass is increasing. In other cases, we had a finite gas reservoir. So when you accrete gas from onto the protostars, it is removed from the gas mass. And we considered position-dependent models, where we basically assumed that the accretion follows the Plummer profile, and position-independent ones. And the same goes time-dependent models, where when the gas mass was reduced, then the accretion rate was decreasing accordingly, and others where the accretion rate was independent of time. We took mass-radius relations from the protostar, where we used both results from the group of Hosokawa et al. And from the work of Hämmerle et al. Both of them were yielding very similar results. So their models, or the impact of the models, is quite consistent. Now here on the top left, you see what happens for our reference model. This is a model where we have a Plummer radius of 0.1 parsec, an initial gas mass of 10 to the 5 solar, and a protostellar accretion rate of 0.03 solar masses per year. And you see that in most of our models, we reach masses of the massive object that are of the order 10 to the 5 solar masses. So a large part of the mass is really going into the most massive object in almost all of the cases. Only in the most conservative model, where accretion is position independent, and then most of the mass is accreted into protostars on the outer parts of the cluster, not in the inner parts, which means that less of the mass is available for collisions. In that scenario, we get a final mass more of the order 10 to the 4 solar masses, but otherwise collisions and accretion are strongly favored, and a lot of the mass goes into the most massive object indeed. This, of course, has a parameter dependence. If we see how it depends on the gas mass, it depends on the model as well. For some models, there's a quite steep dependence. So only when you have really a high gas mass, you do reach very large masses for the most massive object. In others, the dependence is weaker, but to be on the safe side, it's good to assume that you have at least 10 to the 5 solar masses in gas or so. Similarly, there's a dependence on the radius of the cloud. This again depends in a similar way on the model, and for different models the behavior is different, but there's a broad parameter space in principle where one can form quite massive objects. Similarly, if we look at the total number of stars in the cluster, there are different types of power law dependencies depending on n and depending on the model, but none of them extremely steep. So the number of stars is not an extremely crucial parameter. And also for the accretion rate of the protostars, the accretion rate is not a super sensitive parameter. It's a relatively weak dependence on the accretion rate, which in principle is also relatively similar for the different models. Now, of course, there are processes that can potentially inhibit this. One of those is the mass loss in collisions of the protostars. What we find is that even if a small amount of mass is lost during collisions, it matters a lot. This was explored in a project by Patricio Alister, who was running models with mass loss. And what we see here is the final mass as a function of retained mass that we parameterize as f. And this is shown for our different models, again with the standard set of parameters. And you see, even if f is just a little bit smaller than 1, it can have a strong impact on the final masses. This is because, if the most massive object has a high mass and it collides with a low mass object, then at some point even a small percentage of mass loss can lead to more mass loss than mass gain, and then it stalls the growth. It reduces the mass growth in a very significant manner. And as we see here, it can make a strong difference with regard to the final mass of the most massive object. And there are other feedback processes that can also be important, especially if the metallicity is non-zero, if it is rather high. What you see here in this plot is a comparison of mass loss rates by winds. The mass loss rates are the solid lines for different metallicities, as you see here. And this is compared both to the Bondi-Hoyle accretion rate and also the Eddington accretion rate. If we really have Bondi accretion, the winds eventually don't matter. But if the accretion rate is more like Eddington, then if the metallicity is too high, then the mass loss by the winds is just more important than the accretion. And indeed, there's an additional and even more important process, that's the energy deposition of the winds into the gas. And you see here the deposited energy in 1 megayear, depending on the mass of the star that you consider. But if you form very massive stars, you will deposit a lot of energy, which can then easily unbind the cluster, so that you will lose the gas. And that's a very limiting factor in these models that at high metallicity has to be considered. Yeah, with this I'm already at a summary. I will stop here to keep in time. Thank you very much.